Hello there. Thanks for joining us today. I have your resume here, and it looks like you have about 5 years of professional experience with Flutter and Dart. We are looking for someone who can not only write code, but also lead modules and design systems that scale. To get us started, why don't you give me a high-level overview of your experience and the kinds of technical decisions you've been driving lately?
Thanks for having me. It is a pleasure to be here. Over the last 5 years, I have moved from focusing on individual feature implementation to taking a much more architectural role. In my most recent projects, I have been responsible for designing the overall state management strategy and defining the modular structure of the applications to ensure that multiple teams can work on the same codebase without stepping on each other's toes. I spend a lot of my time now on things like reducing technical debt, optimizing the rendering pipeline for complex UIs, and ensuring our CI/CD pipelines are efficiently handling automated tests and deployments. I try to approach every feature from a scalability perspective, asking not just how we make it work now, but how it will behave when we have 10 times the data or a significantly more complex user flow.
That sounds like exactly the level of thinking we need. Let's dive into the technical side. Flutter is known for its performance, specifically aiming for that 60 frames per second target. For someone at your level, I want to know if you understand what is happening under the hood. How does Flutter actually achieve 60 FPS, and can you walk me through the phases of the rendering pipeline?
Right. The core reason Flutter can hit 60 FPS is that it doesn't rely on the native platform's UI components. Instead, it uses its own rendering engine, which is currently Impeller or Skia depending on the platform. Because Flutter draws directly to the screen, it eliminates the expensive communication overhead that usually happens when a framework has to talk to the native OS to request a widget change. To maintain that speed, Flutter follows a very strict pipeline. It starts with the animation phase, where a trigger like a timer or a user gesture starts the process. From there, we hit the build phase, which is where the widget tree is constructed based on the current state. Once the tree is ready, the layout phase kicks in. This is where the framework calculates the exact size and position of every element. After layout, we move to the paint phase, where the visual look of the widgets is recorded as a series of drawing commands. Finally, we reach the compositing and rasterizing phase. This is where those commands are actually turned into pixels on the physical screen by the GPU. If any of these phases take too long, we drop frames, which is why optimizing each step is so critical.
That is a great breakdown. You mentioned the GPU and rendering. One common issue we see in production, especially on Android or older iOS versions, is shader compilation jank or that first frame freeze. How would you go about diagnosing that, and more importantly, how do you optimize it for a production release?
Shader jank is a classic problem. It happens because the graphics driver has to compile the shaders for complex effects, like rounded corners or gradients, the very first time they appear on screen. This causes a momentary freeze because the CPU is waiting for the GPU to finish that compilation. To diagnose it, I usually start with the performance overlay and the dev tool's CPU profiler. I look for frames that exceed the 16 millisecond window. The dead giveaway is if the jank only happens on the first run of an animation and then disappears on the second run. That tells me it is definitely shader compilation and not a logic bottleneck in the Dart code. For optimization, the modern solution is moving to the Impeller rendering engine. Impeller precompiles shaders at build time, which virtually eliminates this issue. Since it is now the default for iOS and rolling out for Android, that is the first line of defense. However, if I am working on a platform where Impeller isn't an option yet, I implement the shader warm-up process. I run the app using the SKSL warm-up flag to capture a snapshot of all the shaders used during a test run. I then bundle that snapshot with the production app. This way, the GPU knows exactly how to render those effects before the user ever sees them, ensuring a smooth first-time experience.
Very thorough. Let's shift gears to data and state. In a real-world app, you're constantly dealing with asynchronous data. Could you explain the difference between a stream builder and a future builder, And give me some specific scenarios where you would choose one over the other.
Sure, both are essential for building UIs that depend on async data, but the fundamental difference is the frequency of the rebuilds. A future builder is designed for a one-time request. You use it when you are asking for a single piece of information that won't change while the user is on that screen. For example, if I am fetching a user's profile page or a specific document from a database, I use a future builder. Once the data arrives, the widget builds one last time and that is it. A stream builder, on the other hand, is for continuous data sources. It is designed to listen for a sequence of events over time. I would use a stream builder for a chat application where messages are arriving in real time, a stopwatch, or a listener for a Firebase real-time database. Every time the stream emits a new piece of data, the stream builder triggers a rebuild of the UI to reflect that change. So the rule of thumb is, if you need a single answer, go with future builder. If you need a constant flow of updates, stream builder is the way to go.
And following up on that, how do you actually handle the fetching process? If you're hitting an API, what is the pattern you use to ensure the UI doesn't freeze?
The key is to never block the main UI thread. I use the async and await keywords in Dart to handle the network request in a non-blocking way. Typically, I wrap the API call in a separate service method that returns a future. Then, within the widget, the future builder manages the state of that request. Because it provides a snapshot of the current state, I can easily check if the connection is still waiting, if it has returned an error, or if the data has successfully arrived. This allows me to show a loading spinner or a shimmer effect while the data is being fetched, keeping the app responsive. If I were doing this at scale, I would move that logic out of the widget and into a business logic layer, like a BLOC or a provider. So the UI is just reacting to state changes rather than managing the network call itself.
You mentioned BLOC and provider. State management is always a hot topic in Flutter. At your level of experience, you've probably tried a few different patterns. How does Flutter handle state management generally, and what are the trade-offs between something like GetX, provider, and Riverpod?
Generally, state management in Flutter is just about tracking data that changes over time and telling the framework which parts of the UI need to be redrawn. I always distinguish between ephemeral state, which is local like a toggle switch in a form, and app state, which is global like the authentication status of a user. When it comes to the libraries, the choice really depends on the project's needs. GetX is very popular for rapid prototyping because it is a full framework. It handles state, routing, and dependency injection all in one. It is fast to write because you don't need build context to trigger updates. However, from a senior architectural perspective, GetX can be dangerous. It relies heavily on global singletons, which can make testing difficult and lead to messy code if the team isn't very disciplined. Provider is the more traditional approach. It is essentially a wrapper around inherited widget. It is stable, follows the standard Flutter patterns, and is officially recommended. The main downside is that it requires build context. If you need to access your state from a place where you don't have a context, like a background service, provider becomes clunky. Then there is Riverpod, which I consider the successor to provider. It solves the context problem by storing the state in a global provider scope. This makes it compile safe and significantly easier to test because you can override providers in your tests. The trade-off is a slightly steeper learning curve and a bit more boilerplate than GetX, but for a professional, scalable app, the safety and testability of Riverpod usually outweigh those costs.
I agree on the testability aspect. Speaking of the widget tree, you mentioned build context. It's such a fundamental part of Flutter, but it can also be a source of bugs. Can you discuss the implications of using build context, and give me an example of where relying on something like context find ancestor widget might lead to an unexpected crash or bug?
Build context is basically a handle to a widget's location in the tree. It is how a widget knows who its parents are and how to look up things like themes or media queries. The biggest risk is that the context is tied to the lifecycle of the widget. A common bug occurs when you have an asynchronous gap. Imagine you start an API call, and while the app is awaiting the response, the user hits the back button. The widget is disposed of and the context is now invalid. If your code then tries to use that context to show a snack bar or navigate to a new screen after the await finishes, the app will crash because you are trying to use a context that is no longer in the tree. As for Find Ancestor widget, the risk there is that you are making a hard assumption about the structure of your widget tree. If you rely on a specific ancestor being present, and then another developer wraps that widget in a new container or moves it to a different part of the app, Find Ancestor widget might return null or find the wrong ancestor. This leads to runtime errors that are hard to catch during development because they only happen in specific UI configurations. I generally prefer using providers or dependency injection to pass data down rather than traversing the tree manually.
That makes total sense. Let's talk about the basics for a moment, just to ensure we're aligned on the fundamentals. If you have a list of items to display that can scroll, what widget are you using, and how do you handle it if that list becomes very large?
For a scrollable list, I always go with list view. If the list is small and static, the default constructor is fine. But for any professional app where the list could be long or infinite, I use list view builder. The builder constructor is critical for performance because it implements a lazy loading mechanism. It only renders the items that are actually visible on the screen. As the user scrolls, Flutter destroys the widgets that move off screen and builds the new ones coming into view. This keeps the memory footprint low and prevents the app from lagging, regardless of whether the list has 10 items or 10,000.
Now let's go back to the internal architecture. You've described the rendering pipeline, but can you give me a conceptual walkthrough of how a widget actually becomes pixels? I'm talking about the relationship between the widget tree, the element tree, and the render object tree.
This is one of the most elegant parts of Flutter. It is a three-tree system. First, we have the widget tree. It is important to remember that widgets are just blueprints. They are lightweight, immutable configurations. When you change a color or a text string, you aren't modifying a widget. You are creating a new blueprint. Then we have the element tree. The element tree is the manager. It maps the widget blueprint to a specific location in the hierarchy. It is the persistent part of the system. When a widget is rebuilt, the element tree compares the new widget to the old one. If the type is the same, it just updates the properties rather than destroying and recreating everything. Finally, the element tree creates the render object tree. These are the heavy lifters. The render objects are where the actual math happens. They calculate the exact size and position of the widget through the layout process. Once the layout is finished, the render objects record the drawing commands and send them to the engine, like Impeller or Skia, which then tells the GPU to paint the pixels on the screen. This separation is what allows Flutter to be so fast. It only does the expensive render object work when absolutely necessary.
Speaking of identifying widgets, what is keyed functionality? Why would you use a key instead of just relying on the widget type in a list?
Since the element tree uses the widget type to decide whether to update or replace a widget, problems arise when you have multiple widgets of the same type in a list. If you have a list of items and you reorder them or delete one, Flutter looks at the types and might think that the second item is now the first item. If those widgets have internal state, like a text field with a cursor or a checkbox, the state might stay attached to the wrong widget. You end up with a bug where the checkbox for the second item is suddenly checked even though you clicked the first one. By adding a key, you give the widget a unique identity. You are telling Flutter, don't just look at the type, look at this ID. This ensures that the underlying state stays attached to the correct widget even if its position in the list changes. It is essential for any dynamic list where the order or content can be modified.
Let's touch on the Dart language itself. You've worked with Dart for 5 years now. How has the introduction of sound null safety improved the development process, and how does the type safety system in general prevent runtime crashes?
Sound null safety was a massive game changer for the ecosystem. Before it, any variable could be null, and you would frequently run into the dreaded null pointer exception. You would call a method on a variable, and if it happened to be null, the app would just crash in the user's hand. With sound null safety, the compiler forces you to be explicit. You have to decide if a variable can be null or not. If you declare a variable as a non-nullable string, the compiler will physically prevent you from assigning null to it. This shifts the discovery of errors from runtime to compile time. Beyond just preventing crashes, this allows the Dart compiler to optimize the code. Because it knows for a fact that a variable will never be null, it can omit null checks in the machine code, which results in better performance and smaller binary sizes. It makes the codebase much more predictable and reduces the amount of defensive coding you have to do.
I'm interested in how you handle code reusability. In a large project, you often find yourself needing the same logic across different classes that aren't related. How do mixins help with this, and how do they differ from traditional inheritance?
Traditional inheritance is a vertical relationship. A class inherits from one superclass and gets all its properties. But in a complex app, you often have behaviors that need to be shared across unrelated classes. For example, you might have a validation logic for a form and a similar validation logic for a settings page, but those two classes shouldn't necessarily share the same parent. Mixins allow for horizontal code reuse. A mixin is a class that can provide a set of functions and properties to other classes without requiring a strict parent-child relationship. In Dart, a class can only inherit from one superclass, but it can use multiple mixins. This allows me to plug in specific behaviors, like a logging mixin or a validation mixin, into any class that needs it. It avoids the problem of deep, confusing inheritance hierarchies and keeps the code modular and dry.
Let's go back to performance. We talked about shader jank, but what about general UI lag? Can you describe a scenario where calling setState repeatedly might cause performance issues, and how would you fix it?
SetState is powerful, but it is a blunt instrument. When you call setState, you are telling Flutter to rebuild the entire widget and all of its children. If you do this in a high-frequency loop, or inside a listener that fires dozens of times per second, you create a massive bottleneck. For example, if I have a custom animation or a gesture detector that tracks a finger movement, and I call setState on every single pixel of movement, the app will spend all its time recalculating the layout and repainting the screen. On a high-end device, you might not notice it, but on a mid-range Android device, you will see dropped frames and a choppy interface. To fix this, I first try to narrow the scope of the rebuild. Instead of calling setState at the top of a large widget, I wrap the specific part of the UI that needs to change in a smaller stateful widget or use a value-listenable builder. This way, only the tiny piece of the UI that actually changes gets rebuilt, leaving the rest of the tree untouched. If it is a very complex animation, I would move toward using an animation controller and a repaint boundary to isolate the painting area from the rest of the application.
That's a good approach. Now for a more advanced architectural question. Sometimes you need to go beyond what Flutter provides out of the box. Can you describe the platform channel mechanism? When is it actually necessary to write manual platform channels instead of just using a community package?
Platform channels are the bridge between the Dart code and the native host platform, whether that is Android or iOS. Since Flutter is its own engine, it doesn't have direct access to the hardware or the native OS APIs. The mechanism uses a method channel. You define a unique name for the channel, and then the Dart side sends a message with a method name and some arguments. On the native side in Kotlin or Swift, there is a listener that catches that message, executes the native code, and sends the result back through the channel to the Dart side. In most cases, I prefer community packages because they are maintained and tested. However, manual platform channels become necessary in three main scenarios. First, if you need a system feature that is too niche for a public package. Second, if you are integrating a proprietary native SDK from a vendor that does not provide a Flutter plugin. And third, if you need extreme performance for a specific native operation that the existing plugins handle inefficiently. As a lead, I always weigh the cost of maintaining custom native code against the convenience of a package.
Let's talk about layout. One of the biggest challenges in mobile is the variety of screen sizes. If you have a complex UI, How do you ensure elements maintain their relative positioning regardless of whether it is a small phone or a large tablet?
I avoid hard-coded pixel values at all costs. If you set a width to 300 pixels, it might look great on a Pixel 7 but terrible on an iPhone SE. Instead, I rely on flexible layout widgets. I use expanded and flexible within rows and columns to distribute space proportionally. For more complex scenarios, I use Layout Builder. This gives me the constraints of the parent widget, allowing me to calculate dimensions as a percentage of the available space. I also use the aspect ratio widget to ensure that images or video players maintain their shape regardless of the screen width. For spacing, I use relative values or a standardized spacing system based on the screen's density. If the design is drastically different between mobile and tablet, I implement a responsive wrapper that switches the entire layout based on a breakpoint, essentially moving from a single column to a multi-column layout for larger screens.
Last technical question for you. I want to see if you can distinguish between two lifecycle-related events. What is the difference between calling setState and the framework calling didChange dependencies?
This is a key distinction. SetState is a manual command. You call it when you know that the internal state of a widget has changed, and you want to trigger a rebuild of that specific widget and its children. It is used for things like updating a counter or changing a toggle. didChange dependencies, however, is a lifecycle method called automatically by the framework. It triggers when a dependency that the widget relies on changes. A classic example is the theme or the locale. If the user changes the system theme from light to dark, the framework calls didChange dependencies for every widget that depends on the theme. The crucial difference is that you cannot manually call didChange dependencies to force a rebuild. It is an event listener managed by the framework for external data changes, whereas setState is your way of telling the framework that internal data has changed.
All right. That covers the technical deep dive. You've given very detailed and thoughtful answers. Before we wrap up, do you have any questions for me about the team or the specific challenges you'd be tackling here?
I do. I am curious about how the team handles technical debt as you scale. When you are moving quickly to hit a release date, it is easy to take shortcuts. I would love to know if you have a dedicated process for refactoring, or if that is integrated into the feature sprints. Also, I am interested in how you approach testing for your complex UI flows. Are you primarily using widget tests, or are you leaning more toward integration tests with something like Patrol or Flutter Driver?
Those are excellent questions. We actually allocate about 20% of every sprint specifically to technical debt and refactoring to prevent the codebase from becoming brittle. As for testing, we have a pyramid approach. We have a lot of unit tests for business logic, a solid layer of widget tests for the UI components, and we are currently migrating our end-to-end tests to Patrol because it allows us to handle native platform dialogues much better than the standard driver.
That sounds like a very mature approach. I appreciate the transparency.
Great. Well, it has been a pleasure talking with you. We have a few more candidates to speak with, but we will be in touch very soon regarding the next steps. Thanks for your time today.
Thank you. I look forward to hearing from you. Have a great day.